Ever just look at the device you're watching this on? I mean, it really feels like magic, right? But what if I told you that deep down at its very core, it's just a massive collection of billions of tiny little switches, and each one can only do two things: be on or be off. That's it. So that's the giant puzzle we're going to solve today. How does something so incredibly simple power our unbelievably complex digital world?
Let's just dive right into it. This is the big question, isn't it? How do you get from a simple on or off to doing complicated calculus, or streaming a movie, or even creating art? It seems like a totally impossible leap. But the answer? Well, it's one of the most elegant and powerful ideas in the history of technology. You see, the whole problem really comes down to a language barrier. On one side, you've got us, humans. We think with 10 digits, 0 through 9. We call it base 10. But on the other side, you have the computer. It only gets two things. Is there electricity or isn't there? On or off? That's its entire language. We call it binary or base 2.
And the most basic letter in this new language is the bit, which is just short for binary digit. It is the absolute smallest piece of information a computer can possibly handle. A single 0 for off or a single 1 for on. Every photo you've ever taken, every song you've ever heard, it's all just a mind-bogglingly long string of these simple ones and zeros.
Okay, so first things first. How do you take these simple little ones and zeros and get them to represent all the numbers that we use every single day? Let's take a look at how the pioneers of computing cracked this very code.
And the solution they landed on is, well, it's pure genius. The binary system. Think about how our own decimal system works, right? We have a ones place, a tens place, a hundreds place. Binary does the exact same thing, but instead of powers of 10, it just uses powers of 2. So you have a ones place, a twos place, a fours place, an eights place. You get the idea. And just by turning these bits on or off, a computer can add up their values to represent any number you can possibly imagine.
Okay, so positive numbers are sorted. That's a huge step. But wait a minute, what about the other half of the number line? This was the next big headache for engineers. How in the world do you represent a negative number when all you have to work with are ones and zeros? It's not like you can just stick a minus sign in front of a bit. And, it turns out there wasn't just one single answer. A few different ideas popped up, each one with its own really clever way of solving the problem. You can almost think of them as different dialects for trying to speak the word negative in the language of binary.
Now, the first and probably most intuitive idea was something called signed magnitude. And the logic is really simple. You just take the very first bit in a binary number and you reserve it. You make it a sign bit. If that bit is a 0, the number's positive. If it's a 1, the number's negative. The rest of the bits are just the number itself. Super easy for us to read, right? But, as we're going to see, what's easy for humans isn't always the most efficient for a machine.
Okay, let's be practical for a second. We live in a decimal world. When you punch the number 7 into your calculator, you expect to see a 7 pop up on the screen, not 01111. So how do computers manage to bridge that gap and handle our numbers the way we see them?
The solution is this really clever system called binary coded decimal, or BCD for short. And what it does is, instead of converting a whole number like, say, 57 into one long binary string, BCD just takes each digit, the 5, and the 7, and gives each one its own private 4-bit binary code. It's a fantastic and crucial bridge between the computer's native language and ours.
All right, now we get to what I think is one of the most brilliant, most efficient little tricks in all of computer engineering. Seriously, this is where things get really clever.
You got to think about efficiency, right? Building a circuit that can add numbers is already pretty complex. Building a whole separate circuit just for subtraction, that would be a huge waste of silicon, of time, of money. So the billion-dollar question for early engineers was this: could you somehow make a single adder circuit do both jobs? And the answer was a huge yes, thanks to this beautiful little process. So the problem is that direct subtraction is really hard for hardware to do. But the big insight was realizing that a minus b is mathematically the exact same thing as a plus negative b. The solution then was to use a system called complements to find the binary version of that negative number. And the payoff? Suddenly, every single subtraction problem is just an addition problem. It gets handled by the exact same circuit. This one trick is an absolute cornerstone of modern processors, making everything faster and cheaper. It's just brilliant. And this is where those different ideas for negative numbers come back into play. See?
Both 1's complement and 2's complement can pull off this magic trick. But in the end, 2's complement won the race and became the modern standard. Why? Simple. It's just faster and more efficient for the hardware. 1's complement had a couple of weird quirks, like having 2 different binary patterns for the number 0, and it needed this extra time-consuming step in the math. 2's complement fixed all of that, and it simplified the circuitry. And in a world where nanoseconds matter, that tiny advantage is a total game changer.
So we've figured out how to represent our numbers, both positive and negative, and we've even found a clever way to do math with them. But what happens when that data gets scrambled? Let's talk about the digital safety net that keeps all our information from falling apart.
What's really wild is just how fragile this digital data can be. I mean, a tiny surge of electricity, a stray cosmic ray from deep space, literally, that can happen. Any random noise can flip a single bit from a 1 to a 0 or vice versa. And as you can see here, that one tiny change can have massive consequences. The number 22 instantly becomes 18. An instruction to save a file might become an instruction to delete a file. It's a huge, huge problem.
So this presents a massive challenge, right? With billions of bits flipping millions of times every single second, how on earth can a computer possibly catch one single error in that storm of data? How does it police itself?
Well, one of the earliest solutions is the parity bit, and it is just beautifully simple. All you do is add 1 extra bit to your string of data, and its only job is to be a tripwire. The 2 computers agree ahead of time. Hey, will the total number of 1s in our data always be an even number or an odd number? Then if a chunk of data shows up and it breaks that rule, bam, an alarm bell goes off. An error has been detected.
But here's the catch with parity. It can only tell you that an error happened, not where it happened. And that's where things get even more sophisticated. Think of parity as a simple fire alarm. It just tells you there's a problem. A much more advanced system, called Hamming code, is like a full-on sprinkler system. It can not only detect that a bit is wrong, it can mathematically pinpoint exactly which bit is wrong and then fix it automatically all on the fly. It's incredible.
Okay, so let's just take a step back and put all these amazing pieces together so we can see the whole incredible picture.
So here's the bottom line. Computers speak in binary, that simple language of just 1s and 0s. They use these clever systems like 2's complement and BCD to translate our world of numbers into their language. They perform an incredible magic trick to make subtraction just a form of addition. And then they protect all of that precious data with a digital safety net, using these error-checking codes like parity and, even better, Hamming code.
It really all comes down to this one incredibly powerful idea. From the most basic, simple concept you can imagine, a switch being on or off, we have built an entire sophisticated language. It's a system of elegant, efficient rules that makes the mind-bending complexity of our modern digital world possible.
We've just decoded the fundamental language of machines, a language that was literally born from pure logic and electricity. So the final question, the one I want to leave you with, is this. As these machines become exponentially more powerful, what will they learn to say next?